Welcome to Feynman's Technique. Today we are going to do a kind of monster integral. Integral from 0 to 1 x squared cosine ln x times ln squared x dx. Wow, this integral, if this indefinite integral, it will be very torture to do this, but it will be very torture. Yeah. But how can we do this in definite integral? Indefinite. These two words are split. Indefinite. How can we do this in definite integral? So first, we are going to let I of a. We indeed used to use our Feynman's technique here, but first thing we are going to do x power of a. Let the function to be x power of a cosine ln x dx. After we get the form of this and then we differentiate 2 times, you will get x power of a cosine ln x. First, differentiate x power of a in the able, you get ln x. Differentiate this once again, you get ln square x, because ln x times ln x. And then we are going to get, if we differentiate this function 2 times and plug 2 into it, it's just our original answers. So you may not understand what I'm talking about. Let's just start. So cosine ln x. Here we are going to use the real part of this. How to do the real part? Cosine, whenever you see cosine, just use the real part. The real part, let me explain it. It's come from the Euler's formula. E power of ix is equal to cosine x plus I sine x. So in this function, when someone asks you what's the real part, use the RE sign. RE of e power of ix. The real part is pretty much just get cosine x, because it's just a real number cosine x. Not a number, but a function, real function. So when someone asks you what's the imaginary part of e power of ix, you can use the simple as im. Im of e power of ix. And look at this, which is equal to sine x. So here, cosine ln x, whenever you see cosine, you pretty much just use the RE. RE of e power of I ln x. This time we say ln x, so we gotta use the ln x, which is equal to cosine. Use a formula, you pretty much just get cosine ln x, the real part of this. So we know cosine ln x is equal to this now, but we can simplify it even more. Use the ln properties, put the I into it, into the ln, write this as ln x power of I. So e and ln you can cancel. So you can get RE, the real power of x power of I, is equal to cosine ln x. Yeah. Whenever you see cosine ln x, you can just use x power of I. Whenever you see cosine some constant times ln x, you can do x power of IA. Yes. But this time you just get here cosine ln x and not the. And we don't have anything be in front of the ln x, so you can just use the RE. RE of x power of I, the real part of x power of I. So we also have a properties. You can put the RE outside the integral. I'm not going to prove that identity in this video. So put the RE outside and then x power of a times x power of I. So you can get the real power of this integral. Yeah. And then x power of a times x power of I, add up the power, you get x power of a plus I dx. So integrate this, add 1 to the power divided by the new power. So you pretty much just get 1 over a plus I plus 1. But I'm going to put this as the real part and the imaginary part form, a plus bi form. This is the real part, a plus 1 plus I, like that. This one, you're gonna add 1 to the power, but I'm going to write it as a plus 1 plus I as well. Evaluating from 0 to 1. You pretty much just get the real part of 1 over a plus 1 plus I. Yeah, we are going to find the real part of this thing. To find the real part of this thing, look at this real thing and the imaginary thing. We are going to multiply by the conjugate of this, which is a plus 1 minus I. A plus 1 minus I, like that. So you are going to get real part. In the top you get a plus 1 minus I. In the bottom you are going to get a plus I, a plus 1, this plus I times this minus I. You pretty much just get a plus 1 square minus I square, right? I square is negative 1 minus negative 1 is positive 1, so plus 1. This one you are going to get a square plus 2a plus 1, right? So over the denominator you can get a square plus 2a plus 2. So we are going to find the real part of this, which is pretty much just a plus 1 over a square plus 2a plus 2. A plus 1 over a square plus 2a plus 2. However though, unfortunately, this cannot be simplified anymore. So whenever we are doing the derivative, it's gonna take a lot of time. And you need to be really careful about this because you may do the derivative wrong. Yes. Use the Feynman's technique. Differentiate x power of a. You produce the extra L-nix here. Cosine L-nix times L-nix. Because we are differentiating this function in the A rule. Yeah. Which is we differentiate this too. And however, our original question is L1 square x, so we have to differentiate this 2 times. So we differentiate this for the first time first. So differentiate this, use the quotation rule. Square the denominator, and then you get this time derivative of a plus 1, you pretty much just get a 1, not a. And then minus a plus 1 times derivative of this, which is 2a plus 2, right? So we can simplify way more. This you get a squared plus 2a plus 2 minus, what is this though? A. You can put the 2 outside, factor out the 2 outside, and then you get a plus 1 square, like that. 2, because you can factor out the 2 and then a plus 1 times a plus 1, you can get this. This we are going to write this as 2 times a squared plus 2a plus 1 as well, which is multiply inside. You get 2a squared plus 4a plus 2. So this one is just due to this. So don't forget the parentheses. 2a squared plus 4a plus 2. Like that. So we are going to continue. A squared minus 2a squared, you get our negative a squared. 2a minus 4a, you get negative 2a. 2 plus 2, 2 minus 2 you cancel. So you pretty much just get negative our, but we are not going to factor out the a. Just write this as negative, but let me just keep it. It's fine, I think. Negative a squared minus 2a over this square. Oh, we are going to do the second time. I prime a. Cosine L-nix multiplied by the extra L-nix, you get L1 square x. So use the quotation rule once again. Square this, you get a squared plus 2a plus 2 power 4. And then a squared plus 2a plus 2 and then square. Times this. First you get negative 2a and then minus 2. And then you are going to minus this. Minus this thing, you pretty much just get plus a squared plus 2a. And then time. And then do a derivative of this. First we are going to keep the 2, keep the power, and then minus the power. And then use our quotation rule. a quotation rule is just not quotation rule, but what's that called? A chain rule. We are going to get 2a plus 2 here. Wow, so many things we can fit out. This thing, 2a plus 2, 2a plus 2, so many things we can do here. And what's going on? This one, we can write this as -2 times a plus 1, right? -2 times a plus 1 times a squared plus 2a plus 2 squared. And this, after we factor out the 2 and then multiply by 2, which is just plus 4 times a plus 1 times our a squared plus 2a plus 2 times our a squared plus 2a, like that. So, what's the deal here? Yes, I'm going to write this more clearly, which is equal to 4 times a squared plus 2a times a plus 1 times a squared plus 2a plus 2 minus this entire thing, a plus 1 2a plus 2 squared. So here you pretty much just minus this. Yes, look at the numbers in front of a plus 1 of this. But we're going to just factor out the, we're going to factor out 2. First thing, we are going to factor out 2 times our a plus 1 and then time a squared plus 2a plus 2 and then time our, this function is so crazy, I know, sorry. And then 2 times a squared plus 2a. And then we are going to minus, we factor out the 2, factor out the a plus 1. We only get our a squared plus 2a plus 2 here. And then divided by this a squared plus 2a plus 2 power 4. So this and this simplify to be the third power. So you pretty much just get 2 times a plus 1 times something. And then the denominator, which is a squared plus 2a plus 2 power 3. Oh, this thing we are going to multiply by inside. This you get 4a squared plus 4a. Sorry, it's raining outside, so loud. And then minus a squared minus 2a minus 2. So overall you are going to get, this is equal to 3a squared plus 2a minus 2. So 3a squared plus 2a minus 2, like that. So here I messed up here. I get the 1 result 21 over 20, 250. And here, because I write this as 4a squared here. This is my bad here. It should be 2a squared. Yes, 2a squared. So you are going to minus this whole thing. You can get a squared, right? A squared plus 2a minus 2, like that. So overall you can get I double prime a integral from 0 to 1 x power of a cosine ln x ln square x dx, which is equal to 2 times a plus 1, right? 2 times a plus 1 times our a squared plus 2a plus 2. A squared plus 2a minus 2 over a squared plus 2a plus 2 power 3. Yeah, you can finally put a 2 inside. The original integral we are going to find is just this. And we can also check whether this function can be factorized or not. 1 to -2. We get some rational numbers, so this function cannot be factorized anymore, I think. So this one is just equal to I double prime 2. So put 2 inside it. 2 plus 2 is 2 plus 1 is 3. And this one we are going to put 2 inside. 2 square plus 2 times 2 minus 2, which is 6. in the bottom, which is 2 squared plus 2 times 2 plus 2 power 3. You can get 1000 in our denominator. So use our calculator, divided by 1000. This is just our result we get in our Wolfram Alpha, which is 9 over 250. Yes. So our result is 9 over 250. Whoa. Finally, why this time? Yeah. Just ignore this. Ignore this. Ignore this. This is the wrong result. Because I've written this 2a squared as our 4a squared. So the entire result just changed. So whenever you are going to do some Feynman's technique questions, or you are going to do the derivative questions in your test or exam, you need to be extremely careful, because you just get a different result, 21 over 250 and 9 over 250. Yes, be really careful. So I hope you guys enjoyed this video, and bye. Stay tuned for more contests.